All right, so first of all, these are not all the skills that we're going to be working on when it comes to momentum, but for the next couple of days, what we're really going to target is what is momentum qualitatively, means without numbers. Like, what does it mean when we talk about something that has a lot of momentum? How can we think about what knowing the momentum of an object tells us? And that's kind of the biggest piece for what I'm about to talk about, although I'm going to introduce some other things as well, and then you're going to hit this again on Thursday. The next piece, in order of complexity, how do you find momentum for an object at any time? How do you find momentum for more than one object? And how do you find momentum for a system of objects? And those are three different but related calculations. The math in general is super easy. It's arithmetic. It's multiplication and addition, and that's it. The tricky part comes when we start looking at multiple objects at multiple times. So we have to come up with a way of thinking about the quantities that we're looking at because they can change. And then the last piece is actually where we're really going to start getting into the really interesting part of momentum. So if you think back to those thought questions that I asked you yesterday, there was this piece of like, okay, well, if you have a little person and they run into a big person, will bounce off maybe. And it kind of doesn't matter if the big person is moving or not. We figured it out both ways, and it didn't seem to make that much of a difference. Like, little person moving toward big person moving, little person bounces off. Little person moving toward big person standing still, little person bounces off. But if you have the same little person moving towards somebody even smaller, they don't bounce off. So there's this piece of, well, like, how is momentum even helpful if what we're looking at is things that are moving and somehow their mass is involved? It doesn't seem like we have enough information to make predictions, and it turns out that the power of momentum in making predictions lies in looking at changes. Momentum itself is rather unpredictable, but changes in momentum are predictable. And that's what we're going to end up focusing on mathematically. So, today, we're going to do this math. I'm going to show you this math. But for now, what I want to do is just really focus on this piece. How can we, what is momentum? And then how can we quantify it is going to be part two of what we talk about today. So the first thing is momentum is a quantifiable, determinable property of a moving object. And so that means a couple of things. I mean, one is that if something isn't moving, it doesn't have any momentum. So when we looked at our thought experiment yesterday, anytime you have an object that isn't moving, it has no momentum. Now, that intuitively, sometimes people are like, but wait, if I try to tackle somebody and they are really, really big and I'm not all that big, then I can't get them to move, so isn't that momentum? And that is not momentum, that's something different. It's called inertia. We talked about inertia. Newton's first law is all about inertia. And what it says is that objects essentially have a tendency to resist changes to their motion. That's inertia. And what changes an object's inertia is simply its mass. So if you tackle a great big huge person, they don't move if you're not also a big huge person, because their large mass gives them super inertia. And when that person is moving even a little bit, they still have inertia. In fact, they have the same amount of inertia. So some of the behavior that we saw in our thought experiment yesterday has to do with inertia, not momentum. And that's a pretty fundamental distinction. What it boils down to is inertia has only to do with mass. Massive objects have more inertia than less massive objects. It has nothing to do with velocity. Momentum is a property of a moving object. Velocity plays a role, okay? And so if you think about inertia, Newton's first law, as being the tendency of an object to resist changes to its motion, whether that means speeding it up, slowing it down, whatever, momentum is a little bit more specific. Momentum tells us how hard an object is to stop. And now if we think about that thought experiment, we realize, oh, okay, well, yeah, if you look at something that isn't moving, it may have a lot of inertia because it might be huge, right? If a skyscraper has a ton of inertia, it's really difficult to get a skyscraper to accelerate. But you know what it doesn't have? Momentum. It doesn't take any effort at all to get a skyscraper to stop moving because it wasn't moving to begin with. If your goal is to stop something from moving, then what you're really looking at is how much momentum does it have. And we're going to look at this in more detail, but what I want you to think about is how it would actually feel to stop the object. And I know this sounds weird, but sometimes I think about it I think about it in terms of how would it feel with my eyes closed. And so like I think about something like, well, if you have a cart like this, and it was rolling toward you, and you wanted to stop it. Okay, so you've got your eyes closed, and it comes, and then you just sort of like, that was pretty easy. So it didn't have a ton of momentum. How could we give this cart more momentum? Well, there's two ways we can think about making it more difficult to stop, right? Like, what's one way?
Put more weight on it.
Put more weight on it. So if we think about, in this image, this wrecking ball, two slightly different objects. If we think about this wrecking ball, even if it weren't moving very fast, it would still be kind of hard to stop, right? Like you can imagine something moving really slowly, but if it's this heavy, boy, you better be careful. What's the other way we can make something harder to stop? Right? I mean, I think you know, but yeah, Jesus?
Increase its velocity.
Yeah, so the same deal, right? Like, we could all imagine, okay, a wiffle ball, like, that's no problem. You could catch a wiffle ball, you could catch a wiffle ball with your bare hands. But imagine if it was fired from, like, an air cannon. You shoot a wiffle ball out of an air cannon at 200 miles an hour, it's gonna be a little bit more challenging to stop. And then, you know, you can think about both things, right? Like, you can then imagine something really heavy moving really fast. And that's kind of the principle behind, like, a cannon. Cannons shoot big, heavy things at high velocities, and that's why they do so much damage. It's really difficult to stop a cannonball that's been fired from a cannon. It can literally puncture holes in wooden and even you know, like, relatively thin metal ships. So when we think about momentum, this is what we're really looking at. How hard is it to stop? And there's a couple ways we can think about it. There's the mathematical piece, which we'll talk about in a second. But what I really want you to focus on is that conceptual piece. What does it feel like when you're stopping something? What does it feel like when you have to work hard to stop something versus when you have to not work so hard? And as we'll discover mathematically, it turns out there's actually kind of two ways we can stop an object from moving. One is we can exert a relatively large force on it. I mean, you know, like, as long as it's safe. So if we were to load this cart up with super big, heavy books, and then you rolled it toward me, I could still stop it. Like, I can just stop it. I'm not tough, but I'm strong enough that I could stop it just by, like, pushing on it. If it were a car, I wouldn't be able to do that, though. If it were a car moving toward me at a couple miles an hour, I wouldn't be able to just push and stop it instantly. But I could still stop a car that was moving relatively slowly. And the way I would do it is I would push on it while it was moving toward me, and I would just sort of slow it down. I wouldn't have to necessarily push super hard, but eventually it would stop. So we've got two ways to think about how hard an object is to stop in terms of the object. One is, how heavy is it, or massive is it? The other is, how fast is it moving? And we also have two ways we can think about stopping something. One is, we can push with a large force over a relatively short amount of time. The other is, we can push with a smaller force over a relatively large amount of time. And it turns out, both of those things have to do with momentum. One has to do with the momentum of a moving object, the other has to do with a transfer of momentum, a change in momentum. And that's ultimately where we're gonna get. That's kind of like the big picture down the road, couple weeks that we're gonna be talking about. One thing that complicates all of this is that momentum has direction. So as we start looking at momentum of multiple objects and systems of objects, it's gonna get weird. And we have a trick that we're gonna use for thinking about this. But for now, all we're gonna need to do is make sure that we use our established protocol of setting up a frame of reference, picking a direction to be the positive direction, and then make sure that we put negative signs in front of velocities that are in the negative direction. We're gonna deal with one-dimensional motion only. We're gonna have one positive direction, one negative direction. Things that are moving in the positive direction will have positive momentum. Things that are moving in the negative direction will have negative momentum. There's no difference between the kind of momentum it is, it's just the direction. Negative momentum isn't some sort of weird inverse suction momentum, it's just momentum in the other way. And because we kind of talked about this already, I'll go through this part relatively quickly, which is that momentum consists of two things, mass and velocity. And here's the spoiler, it's super easy to calculate momentum. We just multiply an object's mass times its velocity. Theoretically, as long as you're using the same units, you can use any unit of mass, grams, kilograms, slugs, like whatever, it doesn't matter. And you can use any unit of velocity, miles per hour, meters per second, light years per century, like it just doesn't matter. But we're gonna use pretty much exclusively kilograms for our mass and meters per second for velocity, which means our units for momentum are gonna be these weird units, and there is no abbreviation for this, unfortunately. It's gonna be a kilogram meter per second. There is no derived unit for momentum. We don't call these momentums or moments or whatever we might call them, because we just don't. No, there's gotta be a way to do this, but I just don't know what it is. Okay, so this right here is the whole conceptual piece. This is the big piece that I want you to start thinking about, the conceptual stuff, like what is going on, what is momentum, what does it tell us. This calculation is trivial. If I tell you an object's mass in kilograms, now you could all find its momentum. If I tell you the object's velocity in meters per second and the direction, now you could find its momentum from that. So that part is easy. What we're gonna shift to and start thinking about today is what we can do with momentum, why it's interesting and why it's important. And the first thing we're gonna talk about is that momentum can be transferred. So if one object has momentum and it hits another object, then momentum can be transferred between those two objects. Yeah?
Just questions on the slide.
Yeah.
Isn't momentum also referred as P?
Yes, and you'll see, yeah, we'll use that. I'm gonna give you those equations, but yes, the variable for momentum is P. Yeah. So if we have, like, most of you have seen pool or billiards in action, whether you've played it or watched it or whatever, but if you have one pool ball that's moving and it hits another pool ball, then at the moment of that collision, there is some transfer of momentum. And we don't know exactly what's gonna happen, like they might both keep moving, or one might move backward, but what we do know is that the one that wasn't moving before will start moving. It didn't have momentum, and now it does. and that momentum came from the first ball. It gets a little confusing because direction matters. So when you transfer momentum, you can transfer momentum in any direction, three-dimensionally in any direction. When we think about transfer of momentum, to start with, we're just going to be thinking about one-dimensional motion. So we'll think about how much rightward momentum an object has, or how much leftward momentum an object has, and we'll think about those being transferred. I could give some of my rightward momentum to something that I bonk into, or something could give me some of the leftward momentum that it has. So those are the things that we'll look at, the transfer of momentum and the direction of the transfer of momentum. And that is part of what we're going to be looking at today. Because what we're going to see is when you have two objects that are both moving toward each other, moving in the opposite direction, they have the opposite momentum from each other in terms of the sign, right? And the one moving to the right will transfer some of its rightward momentum to the one moving to the left, and vice versa. And that's what we're going to look at is, well, how much momentum was transferred? There's a sign piece to that. The sign of the momentum that's transferred is going to matter. This is largely what we're going to be looking at today with the mathematics. The second piece, which we're going to look at starting next week, so I'm going to go through this relatively quickly because this is just sort of a primer, just getting you thinking about things. The other thing is that momentum can be conserved. And there's conditions to this. Momentum in any one given system isn't always conserved, but we're going to find that it's pretty easy to engineer situations in which, at least over a very short period of time, momentum is largely conserved. And what that means is, if we know the momentum that one object loses, whether it's leftward or rightward momentum or upward or this way momentum, then that momentum will have to be gained by something else or some combination of something else's. When momentum is conserved, if one object has -4 kilogram meters per second of momentum at one time and later on it doesn't, that -4 kilogram meters per second of momentum went somewhere else. Something else has now 4 negative kilogram meters per second more momentum than it did before, or some combination of things has more momentum than it did before. And that will happen both in one and two-dimensional collisions, and that means that when we add up the momentum of a whole bunch of different things, that total amount is always going to be the same. This is just sort of a sneak preview. You don't need to really think about this too much right now. It's out there. You don't even need to really write this down. I just want I want this to be something that you now have heard once, that momentum can be conserved. Next week, we're going to talk about conservation of momentum and the law of conservation of momentum. You'll see a couple equations today, but they're not super complicated to write down. Okay, so if you got stuff written down for this, great. If you don't worry about it. This is on Canvas, but more importantly, we're going to go through all of this in much more detail next week. So Khalil brought up equations, and here are the equations that we're going to use over the next couple of weeks. The first is our momentum equation, and for historical reasons, the variable for momentum is a p. It's p because another word for momentum is impetus, which starts with an I. But we use I for other things, so they use the p, and that's where that's as far as I can go with why momentum is a p, but it is. So p equals m times v. The mass is typically going to be measured in kilograms. Velocity is typically going to be measured in meters per second, which means momentum is typically going to be measured in kilogram meters per second, which is an awkward unit, and there's not much we can do about it. And then when momentum is conserved, we have another equation that will be true. And as I said, it's going to be pretty easy for us to engineer situations where momentum is conserved at least for a small amount of time. And that is this equation right here, which says the sum of all of the initial momentum of a system will be equal to the sum of all the final momenta of that same system. So if you find the momentum of one object, another object, another object, another object, add them all together, if momentum is conserved, those sums will always be the same over time. And that is three-dimensional, so there's a bunch of vector math here and things get really crazy, but we're gonna keep it relatively simple. Our systems are largely gonna be one-dimensional systems, at least at first, and we're only gonna be dealing with two objects, which means that our conservation of momentum equation is typically gonna look like this. There will be some variations of this. We'll look at this more in detail next week. You can write this down if you want. It's not super critical right now, but effectively what this says is the mass of one object times its velocity at some earlier time, plus the mass of a second object times its velocity at some earlier time will equal the mass of the first object times its velocity at some later time, plus the mass of the other object times its velocity at some later time. So if we know the momentum of one object and another object, we add them together, the sum of those momenta will equal the sum of the momenta of those same two objects at a later time. And we can get tricky with this, because the masses of these objects don't necessarily have to stay the same. And the velocities could be two or even three-dimensional. We could add objects, we could have 3, 4, 5, 100 objects. We could potentially be looking at systems in which momentum isn't fully conserved. So there's a whole bunch of monkey wrenches that we could throw into this. But if you think about the virtual carts activity that we were doing yesterday, this is what we were looking at. Two objects, two velocities for each object, and it was a one-dimensional system. Yeah?
Is that a little T
This right here,
Yeah.
that's a tick mark. And the way the variable, the terminology for that is prime. So this would be MAVA plus MBVB equals MAVA prime plus MBVB prime. And we don't have to worry about that stuff right now. But we will later, so. Okay. All right, I'm gonna just show you a couple of videos that, for the most part, these are just fun, to be real honest with you. So let's look at this one.
Oh yeah, I saw that.
Have you seen this?
Yeah.
Yeah, this just cracks me up.
I don't know why.
So first of all, nobody was hurt. Second of all, it doesn't crack me up because of the destruction. You'll see why it cracks me up in just a second. This just kills me though, it's so funny. Figure out, it's not working. Something's not working. It's not working. And that's the part that cracks me up. It's like, well, I'll just keep walking.
It's still walking.
Ouch. So here's what I want you guys to think about here. So that's funny. But there's a couple of things that are really interesting about this in terms of thought experiments, and then there's one warning. Okay, so the thought experiment is, imagine that you went to a lake, and you were sitting on a dock, and there was a little rowboat there, and your friend jumps into the rowboat, and then they try to, they can't get one of the oars in the water. You're on the dock, your friend's in the boat, what do? You take your foot and just move it out, you push it and it goes, right? Really, really easy. Now, make it a bigger boat. Now it's a motorboat. Could you still do it? Well, yeah, actually, most of us, if you're sitting on a dock, could push them. It would be harder, but you could push a motorboat and get it away from the dock. Now, make it a fishing boat. Now, make it a yacht. Now, make it like an ocean liner. And you can imagine with that thought experiment that getting those boats to move away from the dock becomes progressively more and more difficult. That is Newton's second law in action. The force needed to accelerate an object is proportional to the mass of the object. You need a larger force to get something really big to accelerate. Where momentum comes in is when you think about a much scarier situation. Still a thought experiment. Now what I want you to imagine is instead of you trying to get the boat away from the dock, the boat is coming toward the dock and you're trying to stop it. So here's your friend, they're in a rowboat, they come toward the dock, they're moving a little too quickly, you stick your foot out and you stop them. Now they're in, a motorboat. Would you do the same thing? I mean, not if the motor's on, right? But if it's just drifting, like they shut the motor off and it's just drifting in, you just put your foot out. Now it's a bigger boat, like a yacht. Moving slow, but it's bigger and it starts to get a little weirder. Now make it like something big, like this. And what you realize is that even this boat moving incredibly slowly cannot be stopped by the human being. We cannot push on this in the time that it's going to take to collide with the dock and stop it. And the scary thing is that literally thousands of injuries occur every year when people get their arms or legs or even bodies trapped in between a boat that's moving really slowly toward a dock and the dock itself. So there's a cautionary piece here, because we're so used to, well, it's going slow, so it's no big deal. People get severely injured or even killed when really big things that are moving slowly pin them. You can't stop it. Just like nobody could stop that, right? Not even the concrete dock could stop it quickly. So it's funny, but also like, think about this, because this stuff scares me, right? Because our brains don't jump to the conclusion that you have to like watch it. Was that somebody? Okay, and then this next one is also interesting for a different set of reasons. Okay.
Nearly a mile across and over 500 feet deep. For the longest time, it was assumed to be a volcanic crater. It wasn't until the 1960s that it was confirmed to have a more celestial, yet just as explosive origin. 50,000 years ago, as woolly mammoths and giant ground sloths wandered these lands, a massive asteroid collided here. The impact energy was about 10 megatons, equivalent to more than 20 million tons of TNT. Named simply Meteor Crater, it's the first geologic scar ever confirmed to have been created by a collision from outer space. Hundreds of other craters have been identified since, but Arizona's remains one of the most spectacular.
So that's an example of kind of the flip side of the phenomenon, right? We have a very massive object moving slowly, but what if you have a much less massive object moving quickly, right? That is an example of the wiffle ball moving really, really, really fast. And so we'll not be able to deal with those kinds of extremes in here, but we can set up scenarios that are pretty close. So we'll, not close, but that will illustrate those ideas. So we'll kind of be able to extend in our minds where things are going. All right. Here's we're going